But how about you guys? So most importantly, I remind you that to be on the safe side, turn on the captions. I know it's kind of tedious to keep reading from the screen and to follow everything from there, but still, it's a kind of second line of assistance. Because one student said that right from the beginning, from week one, he is having difficulty uh, listening to the sound, listening to my lecture, not because of anything else, but the volume is too low, always. I don't know whether the point again, whether it's coming from my side or coming from his side, but that's why I'm asking you that if you encounter any such problem, just immediately let me know. Okay? Ah, today we are supposed to start with something new and exciting. It's gonna be one of the most critical and important chapter. Memory management. Let me scroll down to see where it is. Must be memory management in a nutshell. Okay. Memory management in a nutshell. As the name suggests, they will try to keep it logically coherent, keeping our focus on the theme of this chapter and learning about the core issues and understanding the basic constructs of memory management. Okay, so there we go. So get started with memory management. In other words, it's all about RAM. We'll get to learn a lot of ideas, a lot of new words. Like in all other chapters, you'll be learning new vocabulary, which are uh, particularly associated with this chapter. Memory management is chapter 3. And we have to also stay prepared that towards the end, we'll be learning. Oh, sorry, I think I forgot to share my screen. Wait a minute. And now you can see it. So there we are, stepping into the new chapter, chapter 3, memory management. So there will be new, as I said, the new concepts, new concepts. Stay prepared for that. New vocabulary, all are very important, and new set of algorithms. These will be your key takeaways. Okay, the concepts, important vocabulary, and steps. One thing I can tell you, and as I mentioned earlier, right at the beginning before we step in, to keep it in a very light-hearted way, since it's a very complex subject, we will approach it in a very light-hearted way. So that will help you not to feel stressed. Memory, the one that we are referring to here, is basically a piece of hardware. Let's get started from the very basic, right? And when it comes to management, So basically, it comes down to how do you manage a hardware. And who is going to manage it? It is the job of the operating system, essentially kernel. And what is operating system? Operating system is nothing but a bunch of codes inside the software. So a software managing a hardware. All right. So it all comes down to software trying to manage a hardware. And whenever this situation arises, I think some of you can still remember because I mentioned this thing before many times. It all comes down to one thing, that is mapping. Essentially, very soon we will get to know that this whole memory management is a game of mapping, a mapping game, to put in a very light-hearted way, and that's it. So, what is mapping? Mapping is a logical interpretation of physical space. Logical interpretation of physical space. That is what we call mapping. And essentially, that is what we are going to study. Right? Some of you are still struggling with this expression. Wait a minute, logical interpretation of physical space. What is it? Okay, let me give you a clear idea. Here in front of you, there's an absolute white space. Of course, something written right in the middle. Now, on this white space, imagine that this is a white space, and I put a dot here. You can see the dot that I've just put. And if I ask all of you, then now could you please give me the coordinates of this particular dot? An empty white space and a dot. And I'm asking you to give me the location of that dot on that white space. What will you do? And I can tell you that if I ask this question to 20 students, 20 students will probably give me a different set of coordinates. You know the coordinates are x and y, x value and the y value. That is basically telling me where it is, its address on the white space. And if I, as I said, if I ask 10 students separately to give me the coordinates for this particular point, always there in the same spot on the same white space, and I can tell you they will give me 10 different or 20 different coordinates. So why will they give me 20 different coordinates? Why give me 20 different coordinates? They will give me 20 different coordinates because their logical interpretation of the physical space is different. Logical interpretation of the physical space is different. So what I mean by that, that I haven't moved this dot or this, yes, this dot, tiny dot, anywhere else. It's still there, and the space is still a fixed space. But when it comes to mapping, the things will be pretty different. Okay, why? Because different people will try to map it in a different way. For example, someone will say that, wait a minute, I have to draw an x-axis and y-axis. This is my y-axis, and this will be my x-axis. So according to me, x, y, the value of x is 0, and y is 0 as well. Someone might like to draw the x-axis or y-axis right here, and the y-axis right here. So according to his mapping, these x and y values, the coordinates will change. And that's it. That's how all of you will probably end up with different sets of x and y. Now, who is right and who is wrong? Well, I dare say all of you are right. Let me wait a minute. Let me try to log in from this.
Now is it clear?
Yes.
Wait a minute. I try again a different way.
That's a problem of technical things. Yes, I think you can hear me, right?
Yeah, yes, we can.
Mm. The point is, well, the moment you can't hear me properly, just alert me. And that's more convenient for me to use the cell phone, but something is wrong and I can't hear your voice clearly. And it's not only with your voice, it's something wrong with my cell phone jack, but or this one. Anyways, we'll fix it later. All right. So now we understand what we mean by logical interpretation of the physical space. Okay? So once we understand the logical interpretation of physical space, and we also understand that that is exactly what we call mapping. Mapping. So remember, as I said, this chapter is memory management. In other words, mapping the hardware to the software is a game of mapping. In other words, a game where you logically interpret the physical space. Okay, let's move in. No memory abstraction. As I said, that we will highlight the important points so that you can construct your own knowledge in a comprehensive way by taking care of the logical and important things. Okay, it must be done in a logical way. So what you're looking at right here is the things that used to happen in the past. For example, when we were running one single program, when we are running one single program, there were no question of process switching. Sorry. There was no question of process sweeping or switching because simply we didn't need it. So, no memory abstraction. Now, that's the word that hits you straight on the face, isn't it? I mean, stepping in. The very first word you see, if you can remember, when we were in the process and thread chapter, the very first word you saw was abstraction. What is process? Process, as we define technically, was an abstraction created by OS, operating system. And again, right here, the very first word that hits you straight on the face is abstraction. As I said, that these are the words you will be finding everywhere. They're used in a very, very casual way anywhere inside computer science and IT. Okay. Now, what does it actually mean, abstraction? Abstraction, as I mentioned before, conceptually, it is, you can interpret it as adding a layer of indirection. So basically, it comes down to Mr. A wants to share something with Mr. B. Maybe Mr. A is sitting at this corner of the room and Mr. B sitting at that corner of the room. Well, they can always have a direct communication, isn't it? Whatever they want to transfer, it can be a direct communication, a direct transfer. Or instead of a direct transfer, they can add a few extra layers. A will pass it on to Mr. C. Mr. C will pass it on to Mr. E, and Mr. E will pass it on to Mr. B. And these extra layers that you are creating, okay, for an indirect communication with Mr. B, these are what we call the layers of indirection or abstraction. But these abstractions, if you dig deeper, try to understand, take a moment to understand the concept, to clarify the concept of abstraction. Why do we do it? These are kind of logical steps that we are taking. In fact, which could be a very direct communication, has now been split up into multiple logical layers. So one logical layer communicating with other logical layers. And these logical layers are what we'll be using right here in memory management later. And that's what we are referring to as abstraction. What is the most common abstraction that we can think of? The most common one that has always been part of the memory management, I think you already know it, is what we call, of course, that came later, not in the early computers. But that was the first time that the first thing came when we had to do something about memory management. And that was address space. I reckon all of you remember that word, address space. That's the first layer of abstraction that you are creating. Abstraction of what? Abstraction of your programming codes. In other words, how do you refer? How do you refer to each line of these codes that you have? Well, to do that, CPU will generate a whole bunch of addresses. And these are all logical addresses that CPU will generate for any program that wants to run on RAM. Or any program which is installed on RAM, installed on your computer or your system. And that is what we call address space. But as we talk about this generation of computer that you're looking at on the computer on the screen, there we didn't need any abstraction because we didn't need swapping or paging or switching for that matter. It used to run only one program at a time. There's no abstraction at all. Okay? Even the early PCs before 1980s were all in these patterns. Right? Not going to spend much time. Although we didn't need this kind of abstraction, but still we needed some. Because after all, there was something called OS, all operating system. there's something called operating system. So now that we have the memory abstraction, in at that time, still we needed something. We still needed something to organize those things in the right way.
Okay, wear it after.
So now the thing that we have to remember, although we didn't have memory abstraction at that stage, but still we have one thing, and that even today is relevant. And what's that? That is the organization of these programming codes on your RAM. OS at the bottom, the memory, and the user program above. OS at the top of the memory, the RAM, and the user program below, and OS at the bottom. So we experimented with this, and eventually we ended up with the last one, which basically, if you look at the picture, it will be very clear. In fact, we have clearly mentioned this thing right there. So we are right in there. This is what we are doing at the moment. This is the one that we are doing and more familiar. Now, as you look at it, some of you might ask yourself this question. Why? Why do we have to organize them? Well, as you look at it, the obvious reason is quite clear, I think, most of your minds. And the reason is we just don't want things to get messed up. We just don't want the OS codes to get mixed up with our application codes, right? We want to keep them separate. But why do we want to keep them separate? The reason is obvious. Because the operating system, of course, the software, it must stay under RAM. It must be loaded in RAM like any other process. They are system processes. Now, these system processes will be treated in a slightly different way than the other ones, than the application processes. We will see very soon these application processes will come and go, get switched. But these OS processes are the drivers that you can see at the top. They must have a dedicated place on RAM. So CPU knows, because every now and then, almost every second, every minute, okay, every millisecond, every nanosecond, CPU will have to refer back to some of those operating system codes to execute certain operations. And so CPU needs to know exactly where they are. And also on top of that, later when we start switching them or swapping, if you keep things mixed up all over RAM, and there's no way CPU can CPU can calculate, the CPU can remember that where exactly which memory address has an OS code and which memory address has an application code. So instead of switching the application code or blocking the application code, it might very well actually block the OS code. And that should be catastrophic. So everything will crash because these OS codes must be kept up and running. Okay, so that is what we are doing. That is what we are trying to achieve by separating these codes. Clear? So there, we started experimenting with multi-programs. And as we remember, in those early days of multi-programming, like in the Unix, right, that supported multiple programs, but each program was single-threaded. We remember that. Those were the early computers. In the early days of multi-programming, we used a different technique. That was what we called partitioning. Now, what is partitioning?
Your mic, sir.
Sorry, sir.
Hey, I was locked out. All sorts of problems. Okay. Did you listen to this one? I know because I'm speaking, I'm not looking at the screen. I mean, of course, I'm looking at the computer screen, but I'm not looking at my cell phone screen. And here I was locked out. So I hope you listened to this one. You understood why we separate. That's what I was explaining, why we separated these codes. The separation of the codes will help the CPU to know exactly which codes belong to the system, software, like operating system, and which codes belong to the application software. All right? That's why we separated these codes. Now, moving on as we are here, in early multiple programs and multi-programming systems, we used to apply partitions. Okay. Now, that partition obviously will protect the code of the OS against the process and protect one process against the other. And that was our objective. Okay. But the problem, as we say, is internal fragmentation. In fact, what we are looking at was, I didn't show you the picture right here. So it was like having the RAM and having 2 or 3 partitions. Each partition will have some codes. But one of the problem with these partitions, as I said, are logical for sure, but quite strict. That means anything that is here can't overflow into this part. So if it is partition 1, this is partition 2. Partition 1 and partition 2 are totally separated. So CPU will read all the partitions separately. Okay, and it was much easier for you to CPU to switch from one to another. Although in those days we didn't use switching, we were using swapping to swap these processes out into the operating system and back again into its partition. So basically, CPU could be switched. But one of the problems with these partitions was, as we say, the internal fragmentation, because the partition size is the same and only one program could be in one partition. Now, when another program is loaded in that partition, it may not take up the entire space of the partition. So there will be a little bit of empty space, for example, inside the partition. And that empty space will be complete wastage of memory. And that is what we call internal fragmentation. Of course, number of programs were very, very limited. So we move on, leaving this thing behind, we move on to what we call memory abstraction. That's the place from where all the important things start in your memory management. The very first word that you are looking at is address space. In other words, the address space is, for those who are for the first time exposed to this word, logical I shouldn't say interpretation, a logical map of codes in a program. Okay, codes means executable instructions. So each line of instruction now can be referenced through its logical address. And this whole set of addresses were generated by whom? CPU. Okay? And this is called the address space of the program. So the address space of the program, in other words, the moment, and it is done even before the program actually transforms into or gets converted into a process. At the time when a software is installed and the program is registered with the CPU, the first thing the CPU will give is to generate a whole bunch of addresses. That ranges from 0 to max. Now, this max value depends on the RAM that the CPU is servicing. Okay, so CPU will generate the maximum, depending on the RAM value, up to a maximum value of address. Now, these are logical addresses. So basically, each part of your program, or as I said, each line of code can now be referenced by CPU by using the program's address space. Okay, this entire thing is a logical address space. Entire thing is what we call address space of the program. Okay, base register, limit register. Remember, In the first chapter, I told you that we'll be talking about in a different context, and here we are. Base register and limit register. So now what is base register and limit register? Keep it simple. There we are. Here's your program. Just imagine this is your program. Okay? And this is the RAM. This is the physical memory or RAM. Now the point is this program has already been given a bunch of logical addresses by the CPU. So the program, when it gets its logical addresses, set of logical addresses, or its address space, it has a feeling that it can run anytime, anywhere on RAM because it has all the addresses. But in reality, that's not true. When it wants to run, it will again have to go back to the CPU and asking for a position. Where exactly? At that very moment, there is enough space. Now, talking about enough space, at this stage, we are dealing with contiguous space. Remember, this is the word that we used in the first chapter. Contiguous memory space. So, CPU will quickly look at it because CPU has an address register of the RAM. And this is what we need to remember. CPU not only maps the program, but on the one hand, generating address space, it also maps the RAM and creates a bunch of logical addresses and stores them in an address register. This is one of the vital registers, one of the most important registers in CPU. And CPU hardly ever lets it go from its hand, from its control. Well, sometimes, like when the DMA is working, then it will kind of share this temporarily with the DMA, but DMA controller. But most of the time, it's under the control of CPU because that's how CPU gets to know everything on RAM. Okay, so that is what CPU has. So what CPU will do when it gets a request from process one and that a program one that wants to get loaded on RAM, and the CPU will quickly take a look at the address register and see exactly at that very moment, exactly where there's enough contiguous space for the program one to get loaded. So that's a bit old-fashioned, but that's it. That's how we get started, because currently and later when we go to virtual memory management, we see that we get rid of these word contiguous. But let's get started with that. Now, as it converts, as it decides, okay, this program will now get started from this address. Now, this address is a physical address, as you can see, it's on RAM. This address is a logical address, a part of the program's address space. But this part of this program's address space, which was 0, the logical address 0, will now get converted to the starting physical address on RAM. And that will be called a base address or base value. Got to get my point. And for each program, each process, each program, when it wants to get loaded, CPU also, in its own way, calculates its estimated length or volume. Now, that's CPU's calculation. That's not your calculation. That's not that you look at your program file and you see it is 25 KB, so you say, oh, it's 25 KB. No, that's an internal calculation that CPU will do to assume how much space these bunch of codes could be needing or should be allotted for them when they go through that abstraction process to get converted from a program, some static codes, into a process, just basically active codes. Okay, that is CPU's decision. So based on that, CPU will write something down. And that is what we call the limit value. I must change the pen. That's what we call the limit value. So we had a base value, and a limit value for all the programs which are loaded on RAM. All of them, they must have a starting point, which is basically the logical address 0 of the address space, and a limit value that is an estimation that CPU did looking at these codes or reading at these codes and how much space probably this program might be needing as a process on RAM. So based on the limit and the base, so basically starting from the base, calculating the limit, it will say this bit of contiguous empty space now belongs to process 1, program 1, which is now become process 1. And it should be loaded right there. And for all these programs which are running side by side, there will be a base value and a limit value. And these values will be stored in 2 CPU registers. One is called base register and limit register. Okay. The base register and limit register loads the physical address when the program begins, and the limit register loads the length of the process. So every time you want to switch it, or basically if CPU is pointing to another program, so the CPU is switched, just like anything else, because remember, register is not a big table. Okay. CPU will have to do the quick calculation at that very moment to know exactly where the program starts on memory address, on the physical memory, and where exactly are its codes located. So that is what they will have to do. Now that is exactly what they will have to do. Right. So we can do it, and we can understand what it was all about. When the process is allocated in the memory, the base register loads the physical address where the program begins, and the limit register loads the length of the process. The address of the process is relative, that is not compiled. So basically, you will quickly understand it. The CPU knows exactly if it is looking for a particular code, then it will go straight to that part to execute it. And it knows where to find it. Now, the point, the interesting point is, the interesting point right here is, how do we do this base registers and limit registers? Oh, the interesting thing that I was about to talk about is, if you can still remember, in the process chapter, we try to define a process. We try to define a process with a wonderful expression. In fact, there were quite a few definitions right at the beginning of the process chapter, and I decided to go for a particular one, which I said that I liked. So I still remember it said, a process is a program executing in its own address space. Do you remember that? A process is a program executing sequentially in its own address space. Now that you know what this thing is, what address space is, and how these processes are running, I think you understand that word, that expression pretty well. Because understanding is most important. Because if you understand it, well, you can reconstruct this kind of definition from your own mind. Okay, that won't be a difficult issue. Yeah. So once we understand base register, limit register, take a closer look at it. So every time, so what happens? Every time it wants to get loaded, there will be double check. The first check is all about whether it is an OS code or not. If it is not an OS code, then go ahead, if it is not a OS code, then go ahead and find its base value or the starting point and move on to find, then recalculate from the base value and the limit value where exactly you'll be finding that particular line of code. So just imagine, as I said, the CPU wants to reference execute a particular line of code. So there will be two checks. First, to know exactly that particular code, that particular address, because that's how it works. That particular address belongs to the CPU or not. So that is the first thing that we will have to understand. And then the next thing that they will have to calculate. So the address that it wants to reference, does it belong to OS? Or does it have an OS code? Or does it belong to that particular program? Okay, because one thing you must remember, that CPU doesn't read your code. CPU works like, well, you may think that CPU is very intelligent, or working in a very intelligent way and reading and executing things here and there. But basically, yes, the CPU is doing everything with a blindfold on its eyes. That means that it's kind of blind. It doesn't know which code it's going to, it's logical, but it's blindfolded. You know what I mean? It's not reading a code before executing it. It simply does it in a mechanical way. And that creates a bit of a problem. Okay, so that's why we have to set up these logical things so that we don't end up by having CPU doing the wrong job at the wrong time. Yeah. Moving on. There's a little bit more of a definition, base register and limit register. Okay. And the problem associated with swapping. The problem that was associated with swapping. So what we have here, we understand that we have base and limit registers. A way to give each process its own private address space. Okay, that was what we called this base register and limit register. Now the question is that what were the advantages and what were the disadvantages? So for the advantages and the disadvantages, as we call them, the advantages, we can see the process can move to new locations in the memory at runtime, which is kind of good. But also, then that gives a kind of extra bit of workload to CPU, and there needs to be some sort of tricks for the CPU to remember where exactly on memory that one really is at the moment, because it keeps switching. Try to understand the difference, because when we were using, in older computers, we're using partitions. So CPU know exactly where to go, because each partition was clearly demarcated and they're not going to overlap. So that means one program in a partition. So if it wants to switch, it will just switch from this partition to that partition. So that means CPU also were very much aware that this is the starting address of that partition and that is the end address for that particular partition. Okay, so it was aware of that. But now it is not possible. So there's a challenge coming up at the same time. Right? So all sorts of things are happening. And that is where the game starts. As I said, then how do you manage all these things? The next one, when it moves, the base register value is reloaded. So that may sound like an advantage, but that in fact can be too much of an extra work for CPU. And that is what we are talking about right here. So we understand that we are in the middle of something that is going to be a little more complex. It gives the biggest advantage that it can now move around from one part to another part. It doesn't have to stay in a fixed place. Although at this very point, we still needed contiguous memory space. That means at least wherever the program goes, wherever on RAM, all its codes must be one after another in a sequential way in contiguous space. So the things at that stage were just started to getting more and more complex. Moving on, the idea of swapping. Okay. Now remember, as we are right here, up to this point, we were using the word switching as well, right? Context switching. Now let me tell you what's the difference. You will be finding swapping and switching intermittently everywhere, but they're different. Switching and swapping. To understand the difference, just imagine that three of you are sitting on a table, on a bench in the classroom, and I'm the teacher. Okay. I am standing with a book in my hand. So what I'm doing, I'm trying to swap them. If I do swapping, I will give the book to the student number one, and then student number one will return it back to me. And then I will give it to student number two, and student number two will then return the book back to me. And then I give it to student number three. He in turn will return it back to me, and I will give it to someone else, or back to student number one or student number two. So this process is what we call swapping. So basically, I'm taking the thing out from you. I gave it to you, and then I'm taking the thing out. Now, to understand it even better, if you can think of CPU working, the CPU, the way the CPU works, and basically the way the CPU works is what the CPU wants to do is CPU wants to give, or rather you can think of the CPU being controlled by the kernel. Okay, so if you think about this CPU being controlled and swapped by the kernel, what will be your idea when CPU is controlling everything to the kernel? So basically, in swapping, there were three processes loaded side by side in RAM. And these processes, when they are not executing, they are getting swapped out temporarily. That means they're moving back to the swap area inside the hard disk. So that is what is happening when they're getting swapped. So basically, 3 programs currently loaded. One of them have CPU. CPU finished execution on them, and then that program was not there anymore, on RAM anymore. It is temporarily swapped out and stored inside the hard disk, in a spatial area hard disk we call swap area. And then again, when the next time it wants to have a CPU, it will be loaded back. So that is how the CPU, this one goes. Okay. So we had swapping and switching. So that was what we call swapping. But now what is switching? Later, in modern computers, we always depend on process switching. So how does switching take place? In switching, we need a controller. So basically, the programs which are currently loaded on RAM, that means they're the process, once they finish their execution, they're not moving out into the swap area or leaving the RAM temporarily. They stay there. All the processes, whether they're executing on CPU or not at that very moment, as long as they haven't finished their execution, they must stay on RAM. And CPU is getting switched from one to the other. And that switching is being controlled by the operating system. So try to understand the difference between switching and swapping. You get my point? So we have the switching and we had the swapping. In older times, we used to use swapping. When you use the swapping technique in older times, so of course, later we will again come back to swapping, but in a different context. We'll be swapping the pages, not the entire program. But in those days, we used to swap the entire program out temporarily. And then again, putting it back on RAM, and definitely this time it will be loaded in a different place. As we said, that was the advantage, sort of having a base value and a limit value, so we could move things around or let the process get loaded in separate places on the RAM. And that's what we were trying to do at that point in time. So we were swapping, right? Now, when it comes swapping, that we will be using 2 words, and you need to remember these 2 words: swap out and swap in. Easy to remember. Swap out literally means that the codes, the programming codes, were swapped out from the memory into the hard disk, and then swapped in, which is basically from memory, from hard disk into the memory. Okay, so there were 2 expressions: swap in and swap out. But as I said, the swap in and swap out, this is what you're looking at, the swapping. But swap in and swap out in those days, well, you are basically swapping in and out the entire program. That created the problem. And the problem is every time they're swapped in, their base value changes. And CPU will have to do an extra bit of calculation every time they're swapped in. from the hard disk. Okay, that is what it will have to do. And that's what you can see right here. And it also gives rise to fragmentation. Unless, of course, you use some sort of a method to address the issue of fragmentation. What you are looking at, say, for example, if you look at picture E. Okay, picture E. The question is, do we have enough space to load another process? It seems we don't have enough space. But if somehow we could squeeze this empty space between B and D and the one at the top of C together, we might end up having enough contiguous space to load the new program. And that is what we call that the problem associated with swapping. That was the problem associated with swapping. Okay. Because we can move things around. Of course, the first problem was to recalculate the base register. But the biggest problem is fragmentation. This is where the memory starts getting fragmented. And that's what we are looking at. That if you want to address the issue of fragmentation, then you have to use a technique which is called memory compaction technique. Memory compaction technique. And that's exactly what we are looking at. Now, you must be familiar with this word compaction, right? Because we still use a piece of a technology that we call CD, right? Compact disk. Why do they call it compact? They call it compact because simply you can't fragment these storages, that CD. Or you can't let it get fragmented. Why? Now you understand what is fragmentation. Now talking about fragmentation, this is another common problem that we will always try to address in memory management. In RAM, on hard disk, you will be finding this word everywhere, this expression, fragmentation. Now one of the ways to address this issue is a compaction technique. Compaction technique literally means there must be a mechanism to address this issue of fragmentation, to stop fragmentation from happening. And the way they do it in the CD, for example, that's the reason why we called it compact disk, and I think most of you are aware of that, although you don't use CD too much or too often these days. You can't delete something from a CD. First of all, when you want to write something in the CD, it's not just a copy. You have to use a special software to burn the CD. To burn the CD. In fact, after burning the CD or after dumping the data right there in the CD, if you take it out and look at the shiny side, it has two sides. That's the glossy side and kind of the dull side. So you look at the shiny side and you can probably see there's a burning mark, okay, that shows that where exactly, in which sectors or which part of the CD has been written with data, has been burned with data. So you can, we used to do it because in our times we had to use CDs quite a lot. Now the point is that we call it compact disk because you can't delete a file, not like your USB flash drive. You can't delete a file. You are not allowed to do that. Well, if you really want to delete a file, you just destroy the CD. That's it. You can't open a file from CD and do some edits and save it directly into the CD once more. No, you are not allowed to do that, because the problem was coming from the contiguous space. If you want to edit a file which is already there inside your CD, well, you can open it and edit it, but when it comes to saving, you save as a new file on your hard disk, and then again burn the new copy as a new file into your disk, into your CD. So we used to call them, and that's the reason we used to call them compact disks. We still call them compact disks because there was a mechanism to prevent that was from happening. Now, the next part, we're actually looking at a different problem. A different problem, and the different problem is that how, remember what we said when we gave the definition of a process. We said it's an abstraction. It's a whole bunch of things getting activated from the static codes. The static codes, as we said, were just kind of the recipe of a cake printed on a piece of paper. But process is more like doing those things, running around to arrange all those ingredients and put them in the proper place and start up your oven, heat it up at the right temperature, make the batter, and all sorts of other activities. Now, when all these activities are concerned, so basically the end of the day, when those codes will be loaded on RAM, those codes, those instructions will be loaded on RAM, they will be active, or they will be behaving in a different way. What I mean is they will be having a data sector. Okay, as I said, that it's up to the CPU to interpret or to estimate that how much space this program might take on CPU, on RAM, when it gets loaded. Okay, so the CPU will have to split it up into 3 parts at least. One part is called a stack, that is usually on top of the code part. Then this next part is the code part, and the code part is the one where all the codes and instructions will be dumped, will be copied. And then we have a data part where all the shared data will be stored. And initially the data part is very thin. Initially it's very thin. That means nothing much in it. Why? Because data part is where the placeholders will be created. For example, right at the beginning of your program, you have declared a couple of variables, integer x, okay, and string y. So integer x means that when CPU reads it, that CPU will reserve a 2 byte, because one integer means 2 bytes. So 2 byte space for it. One string means 8 bytes, if I can still remember clearly. I think 8 bytes, right? So 8 bytes will be preserved for a string. So these memory allocations will take place, and that will be on top of the programming codes. So this is what we call the data part, or the data sector. But the point is, when they start running, they start behaving in a different way. They start behaving in a different. So how do they behave? The way they behave is Now, once we understand that what this data sector it was all about, now moving on, let's see what happens to runtime memory management. So what is runtime memory management? What basically does, what happens is this. The data part, as we said, initially it was minimum. It was minimum. It was just created for those values, to store those values which will come as the program, as the codes get executed. But then as the program starts running, new values are created and the old values get overwritten. So the data sector, the data part, starts growing and keeps asking for more and more space. So that is a common scenario. That is the most common scenario that we encounter. So how do we deal with that problem? Because right from the beginning, CPU calculated and estimated the length of the program. Then according to its estimation, it is already allotted that much, is a particularly limited space, because we are talking about contiguous space, right? A limited space, limited contiguous space on the memory for that particular process. Now that process is on RAM, and during its execution, it is asking for more space because its data sector is growing. Where will the extra space come from? Because remember, these are contiguous allocations. There may be some other spaces here and there, but little too far, because they're at the beginning and the end, there are two other processes next to this particular process. So those little bit of spaces left in memory here and there, well, we can't utilize them as long as we stick to these contiguous memory allocation mechanism. Okay, we can't do anything. So that was the challenge. So what we did was a few experimentation. Allocate a little memory whenever a process is swapped in or moved. Okay, that is one of the things that we did. But even a better solution is has a stack on the top of its abstract allocated memory, which is usually growing downward. That means moving downward, and the other one that is growing upward. So that was what was happening right there. So we could actually somehow manage a little bit of space in between the stack and the data part. Because remember, data part is asking for more space, and the stack is going downward. Initially, the stack was bigger. Now, somehow a little bit of space is generated right in between, and we can probably try to give it to our process. That's the only thing that we could do. But now that was not enough. That's what they mean, looking at the picture. But that was not enough. And I tell you, we started having a problem. The problem, because we passed to that phase and we encountered the problem, and finally we got the solution. So we find everything that we study here quite relevant to our experience. I mean, the things that we experienced. The problem was that, see, for example, this problem used to happen on operating systems like Windows 98, Windows 95. You start watching a video, a movie, In those days, we didn't have YouTube or anything. So it was just a CD probably. And you start playing that movie, you start watching it. Or you're playing games, but still games were not so developed or robust. Because they were just emerging. This game market was just at its startup level. Now, the thing that we used to encounter mostly is during that kind of video, watching a movie. And we are watching a movie, and when we start watching the movie in a Windows Media Player, everything is fine, no problem. 5 minutes later, 10 minutes later, you start feeling that something is not wrong, something is not right in your computer. Your computer kind of slowing down. Okay? But you ignore these symptoms and you continue to watch it. You continue to watch it. And as you continue to watch it, then suddenly, from nowhere, the computer shuts down. Boop, it's all black. That was a crash, and you will get a message most of the time on the memory, on your screen, that memory out of space. Memory out of space. Okay. Now, it raises a few questions. So first of all, why the problem didn't happen right from the beginning? Well, it didn't happen right from the beginning because when you started the app called Windows Media Player, for example, CPU gave it a contiguous space that CPU estimated for this particular program, particular process. Okay. And a little bit of space in between the stack, as we are looking at, its stack and data part, so that that part can be managed and utilized by both of them whenever whoever wants it. But then as you started watching the movie for whatever reason, and it used to happen with movies, and there's a common failures used to happen with movies and games, because for movies and games, you understand that we love them so much, we just don't want to interrupt this. And this keeps going on and on and on and on. And your CPU hardly have any chance to get switched from this app. So basically, you are watching and watching and watching after 15 minutes, and as you keep running it, the data sector is getting written and overwritten and written and overwritten and written and overwritten, and it is growing. And at one stage, there's no more space to grow. It will simply crash. So that was also the problem with some of the very rare in those days, but big application software. Okay, so that was a problem. And because of which, we had to move on to virtual memory management, where our goal is to get rid of these contiguous memory allocation. Okay, we didn't want this contiguous memory allocation. So that is what contiguous memory allocation was all about. And the problem associated with contiguous memory allocation. Bitmap. All right, I will not start bitmap today. Leave it here. Take your time to go slow, the initial state. Read this part of the book. We are still in the memory abstraction part, and we will continue the memory abstraction before we go to virtual memory management. So I suggest at this stage, you read right from the beginning. Don't go to virtual memory management. Don't go to that part from the book, I mean. Okay, stay focused on memory management abstraction, memory abstraction. Understand that part, because remember, what we do with memory abstraction, based on that, we'll be doing something new in virtual memory management. So understanding the first level is very important. Okay. You'll take your quick attendance. Xuan Wang. Xuan Huang. Chi Kang. If
Yes.
any of you miss the attendance and you are still there for your meek or whatever reason, just drop me a message. I will check. Chi Kang, yes.
Yes.
Vinfok,
Yes.
Duc Huang,
Yes.
Luong Ha,
Yes.
Hu Huang,
Yes.
Tan Hum,
Yes.
Nap Phat,
Yes.
Din Min,
Yes.
Din Min,
Yes.
Quoc Huy,
Yes.
YN,
Yes.
YN.
Yes.
Okay, just speak a little bit louder because my. Okay, I think I should. That's Kim Thak,
Yes.
Nhật Min,
Yes.
Tiền Phúc,
Yes.
Quang Huy,
Yes.
Minh Kung, Minh Quang, Duy Bao, Duy Bao,
Minh Cường, yes.
wait a minute. Minh Kung, yes. Duy Bao, Quay Min, Liam Chuk,
Yes.
and Quoc Hum.
Yes.
Okay. Is that Duy Bao and Din Min is here? Yes. All right. Thank you.
Teacher, I'm Xuân Hoàng. Xuân Hoàng.
So where did you come from? Where did you go?
I forget when you call me my name.
Really? All right.
Yeah.
Thank you. Give the book a read right from the beginning. As I said, well, these are the chapters, very important. As we move slowly, you keep updating yourself. So you will understand the discussions. All right. So we will continue with this one, not only in this week, but also next week. All right.